is Dovmund, who came from the University of Adam Mickiewicz in Poznań, and he will be staying with us for a week, working with me on integrating some machine learning into the machine translation toolkit Moses. But today he's here to give a talk about grammatical error correction for English as a second language learners by SMT. So I give the floor to our speaker.
Thank you very much. And the reason why I'm here, I've been writing passive-aggressive emails to Alish from the time, when is your classifier going to be ready, because I want to use it. And the answer, it is sort of ready, but not really usable. And then he had a glorious idea. If you want it to be ready, then just come over and help make it ready, which is actually a very nice idea, and I'm very thankful that you invited me here. So I'm going to talk about grammatical error correction by statistical machine translation without a classifier. So how to get it right when you just use vanilla phrase-based statistical machine translation. This is by no means a new topic. There have been attempts to do that since statistical machine translation has been around. I think the first work was probably around 2006 or something like that. But the funny thing is there are always some details that are off, because the people that try it are not statistical machine translation researchers. So they make certain subtle mistakes. They implement huge features which they claim, oh, this is working so greatly, or another feature which they claim, this is not working at all. While I'll disagree with them a lot, because as I will show you, it turns out that a vanilla Moses system without any special features can beat the top results for the CoNLL shared task if you just do it correctly. So, but actually doing it correctly took me half a year. So it's just do it correctly, but doing it correctly is not really easy. And there will be a couple of lessons. So let's first introduce me what's going on in grammatical error correction. We focus on grammatical error correction for English as a second language, so this is probably interesting for all of us, because none of us is native, I suppose. There's the most significant event recently has been the CoNLL-2014 Shared Task on grammatical error correction. It has been preceded by 3 other shared tasks, the Help Our Own in 2011 and Help Our Own 2012. This was quite interesting because this focused on the correction of scientific articles in NLP, actually. But they only focused on determiners and preposition errors. Determiner errors are probably quite interesting for us. We are mostly Slavic speakers, so we don't have determiners, and getting them right in English is quite difficult. It's a lot easier for me because I grew up in Germany. I just apply German rules blindly to English. Works 99% of the time. But when I have to correct article errors from my PhD students, I see how difficult it is for them. Then there has been the CoNLL-2013 Shared Task on grammatical error correction. They only corrected 5 error types, so again, determiners and articles, prepositions, noun number mistakes, subject-verb agreement mistakes, and verb forms. 16 teams submitted the results, and this year there were 28 error categories, so they stopped filtering, just correct the whole text, and 13 teams participated. The training data and the test data that they made available during the CoNLL shared task has been provided by the National University of Singapore, and it consisted of 1,400 essays written by students from this university, around 1 million words, around 51,000 sentences. Those essays had been corrected by their English teachers, so probably by the help of the Center for the English Language, and annotated with errors, error types, corrections. The topics were environmental pollution, healthcare, aging population, and similar things. And as I said, there were 28 error types. Let's skip to the error types. For instance, most of the errors are article or determiner errors. That's the biggest group with more than 6,000 errors. Then you have mistakes like wrong collocation and wrong idiom, local redundancies, noun number errors, Those marked with a star were the error types that have been corrected on the CoNLL Shared Task in 2013. Prepositions and some obscured errors, which I couldn't even say what a dangling modifier is right now, but they also amount to a very small part of the data. The data looks like this. It's an XML document, annotated essays. You have paragraphs that have been written by a student and annotation. So which teacher did the annotation? Where does the modification start? Where does it end? What type of error we have, and what we should substitute. So for instance, here we say that we should substitute this part, engineering design process, with the engineering design process. So as we see, it's an article or determiner error. What makes things a little bit complicated is you see those are not minimal edits. So since these edits has been performed by non-computational linguists, they're not concerned with things like minimal edits. They just want to, well, maybe add some kind of explanation to it. So it should not be engineering design process, it should be the engineering design process. This makes evaluation a little bit complicated because we have to compute the minimal distances and everything. But luckily there's a metric for that. Whoops, wrong direction. There has been a metric developed for that, the so-called MaxMatch Metric. And it has been used for the CoNLL Shared Task from 2013 and 2014. Before that, they just used diff. And diff was a problem because when they were counting correct edits, do the edits overlap or not, those non-minimal edits could sometimes be not correctly counted. So it might turn out that the evaluation metric was actually missing correct edits. Since this was probably more or less random, it was probably fair among all the systems. The MaxMatch metric kind of fixes this problem. They find the maximum overlap and really count everything that overlaps. So even if we have annotations that are not minimal, this metric is able to find the optimal overlap and count the overlap. And what is also quite interesting, this is an F-score. So it counts precision and recall and reports the F-score. In 2013, they reported F1 score, so precision and recall was weighted equally. For 2014, they realized that maybe precision in a grammatical error correction task should be more heavily than recall, which is a very good intuition, but in my opinion, still not enough, as we will see later. So they are now weighting precision 2 times as much as recall. The intuition behind that, if you have a system that you give your text to, you would rather have errors corrected, even if they are few, than new errors introduced. So this is probably the worst thing that the grammatical error correction system can do, introduce more errors. And as we will see later, remember that sentence. That's a very significant sentence at that moment. How does the metric actually work? The metric gets, again, the input from the CoNLL format, but the CoNLL format has been converted. So now you don't have paragraphs anymore. You have sentences. You have tokenized sentences. This tokenization has been created by the NLTK toolkit, which in my opinion is a mistake. In my opinion, you shouldn't provide or force systems to use a certain tokenizer and a certain sentence splitter. In my opinion, they should evaluate on detokenized data, but that's another question. And here again, everything that's preceded by a S is the source sentence. Everything that's preceded by an A is the token-wise correction. Again, you have information whether this is required or not, which annotator this comes from. So 0 is annotator 0, 1 is annotator 1. So you can have, it's like a multi-reference system basically, similar for statistical machine translation. And it will work in such a way that if you have 2 different annotators for one sentence, it will choose the error rate, the smaller error rate. So it will favor the annotator that gives the higher result if you compare it on sentence level. So there's a similar effect as for multi-reference bleu. If you have many annotators, your scores will go up, just because you just managed to hit some of those reference corrections. And you simply count the number of matched annotations. From that you get a precision, correct edits, proposed edits, and then you divide correct edits by all edits to get precision, and correct by proposed to get recall, or the other way around. I never remember it when I have to when I have to say it from my head. But and in the end, you just compute the F-scores. For this example here, it would be an F-score of 0.8. The Kernel Shared Task results. We also submitted a system, so the third result is actually our system. This is a pure SMT system. The second result is a pure machine learning approach, only based on classifiers. And the first system is again machine translation, but with, I think, rule-based error correction and a huge, ginormous pipeline of I don't know how many re-rankings. And I wouldn't even be able what's in that to tell you what's in that system, because they have I don't know how many steps. What is quite interesting is that we are quite close. At least the top 3 results are really close to each other. While this is basically a very simple Moses system, and all of these are more complicated and task-specific classifiers and everything. And also the interesting thing here is that we did much worse than I was expecting, because we had held-out test data, and on held-out test data we were at least 10% better than anyone else. And on the shared task data, we were, well, still top 3 results, but nothing special. And I didn't find out for another half year why that happened. But this is going to be another lesson from the talk. And the really frustrating is that we could have won so easily. But I just messed up at one point, and it's really just my fault. But we will see. Okay, so what did we do? Well, what did our system? We treated grammatical error correction just as simple translation from erroneous into corrected sentences. Nothing special here. Our baseline was a standard phrase-based Moses setup, and we explored, so we are the first ones to ever do that, how to optimize parameters according to the task metric. Well, the first one within that task, not the first one to do that, because of course everyone else optimizes the metric and the WMT and everything else. We tried to use web-scale language models. Kenneth Haffield's language model just became available during that time. And our biggest mistake was to try to use that monster. It's a 5 terabyte binary file. I don't know whether you ever tried to use it. And with a normal computer, normal, I say, still 128 gigabyte of RAM, it's just not possible to use that. And this was my main problem, which later turned out to be killing our results. We use larger error annotated resources as parallel data. I will talk about that. And we try to invent some task-specific dense and sparse features which would allow us to boost our results a little bit. The data that we used for training data for translation model is just the knuckle corpus that I introduced before, those 57,000 sentences. And a very interesting resource, sentences scraped from a website, Lang8. I will talk about that a little bit later. Language model data was just the same as the translation model data. Then we tried a Wikipedia language model and this huge Common Crawl language model, which actually didn't work out, but later about that. Then another interesting system. This system has been created later, after the Kernel Shared Task, by the Kernel Shared Task organizers. So while they actually got in all the submissions, they were already busy writing their paper. I remember I got an email asking how exactly to set up my system before the shared task was actually published. So, sorry, who are you? Why do you know about that system actually? Because the person forgot to introduce himself, and it turned out that it was the first author who was a PhD student of the main organizer. that really got me worried, because like 2 months before official publication, you get someone who's asking very specific questions about your paper. That shouldn't happen. And what they did is a very interesting idea. They just used Kenneth Haffield's MEMT. This is a tool for system combination of machine translation systems. And they built 4 systems, which were quite similar to the top 1 to 3 systems from the CoNLL Shared Task. And they tried to combine those systems. And what they also did, they tried to combine all the CoNLL for 2014 submissions. For the classifiers, they used additional part-of-speech taggers, chunkers, and so on. So they used a lot of external linguistic knowledge for that. But what is interesting for us is the resources they used for the SMT system. So for the SMT translation model, they used again the knuckle corpus and a published version of Lang8. And for the language model, they use the same information that has been here in the translation model, and a language model only built from Wikipedia, English Wikipedia. So just Wikipedia converted it to plain text and built a language model from that. And as we are talking of resources, we also have to mention the submissions, which could also be seen as resources. So what I will try to do is to build a similar system using this data only, so this would be restricted data then use data that has been used in the CoNLL submission in an unrestricted system. And we will compare how good can we get when we just use Moses without these additional post taggers, classifier stuff, and anything. Just vanilla Moses, if we do it the way I think it should be done. Finally, Lang8. That's a very interesting page. I think it's based in Japan, and it mainly aims at Asian English language learners or second language learners in general. It's like the Facebook of language learners. I correct your essay or your text that I'm proficient in exchange for you correcting my text. So you just have to, when you register, you have to say what is your native language, what are the languages you want to learn. Everyone says that, so you have people that are native in different languages, and if you happen to learn the language that someone else is native in, then he can correct your sentence, collect points, and you can use those points to have his text corrected again. So basically it's a big homework exchange page, I would say, because that's probably what it amounts to. But it's a very interesting resource for English as a second language grammar correction, because you get millions of sentences that has been corrected. So it's slightly smaller. We have a bigger thing here. So you get sentences where you can extract pairs and corrections like that. Red would be incorrect, green would be correct. So the original sentence would be, I thought that they are good combinations between winter and reading, whatever this is supposed to mean. And then you get better correction. Those corrections are never really good. Well, okay, quite often good, but hopefully better than the input, which is already enough for us. And the correction would be, I think there is a good combination between winter and reading. So you get substitutions, you get insertions, you get deletions in this page. And as you will notice, we do not take into account reorderings. Usually this would be a reordering, but we just treat it as an insertion and a deletion that are independent from each other. And concerning the Lang8, there's one resource that's free. So you just need to register, and you get about 2 million English uncorrected corrected sentences from that. And what we also did, we scraped the web page, which is legally and morally a little bit dubious, but it's for science. So from that we got around 4 million sentences. So already more than that. What I definitely need to do, I just need to contact those the owners of the web page and at least ask them for permission or something. So this is also why I'm not using those scraped material anymore. I did use it for the CoNLL Shared Task, but I will probably not use it anymore. I will give it here as an example, but as I said, without permission I probably shouldn't be using it. The language model data that we have and that we try to use is Knuckle again with around 50,000 sentences, then around 2.5 million sentences from the officially available Lang8 data, 200 million from Wikipedia, and 60 gazillion from Common Crawl, which is, I think the compressed text data is some 4 terabytes of data, I think, when it was available for download. And this is cleaned text, so no HTML, anything. Cleaned, deduplicated text. 4 terabytes of compressed data. And, but it's really useful. We'll see that later. So, how do we compare? The first 5 data points are the top 5 systems from the CoNLL Shared Task. We treat them as unrestricted because you are basically allowed to use anything. So people were using Google Ngrams. We were using this non-free Lang8 data, and we tried to use the Common Crawl data. So we have to say it's unrestricted. Also, people used lots of rule-based stuff for that, post-taggers, chunkers, parsers, I don't know what. So definitely unrestricted. Then there is this work from the shared task organizers that appeared during EMNLP. There we have the systems that they built themselves. Those systems are based on the resources that I mentioned earlier. So let's say these are restricted. And they also built the system combinations from the CoNLL shared task submissions. Since those systems were unrestricted, we also have to say that the system combination is unrestricted in this moment. And what is quite interesting here, we see that at least as far as published results are concerned, they have definitely the highest result for a restricted system and the highest result for unrestricted system. Although those results for unrestricted systems are a little bit cheated because MEMT needs to be tuned. And they tuned it on a small part of the test data. So we probably need to say that it would be a little bit lower if they had other tuning data available. But let's accept this result. We beat them anyway. So it's OK in this code. And in this talk, I will also try to build a restricted system and see how far can we go with unrestricted data. The talk is organized into a couple of lessons, things that I had to learn the hard way while preparing the CoNLL data for the CoNLL Shared Task, and also trying to find out what went wrong with our system. Why didn't we win, actually? So I'm trying to answer those questions. Well, the first thing, is this correct? Yeah. The first thing that we learned was that we should implement task-specific features in Moses. Moses is a statistical machine translation system. It's not tailored towards correcting monolingual text. So what we should add in this moment are features that somehow tell the decoder what it is doing in this monolingual context. A very obvious thing to do is to add the Levenshtein distance between phrases. So if we have a phrase table, let's say this is a very small phrase table, we have a source phrase and a target phrase, then we just count, we just give the Levenshtein distance as a feature into the phrase table. The nice thing is, if we add the feature e to the power of the Levenshtein distance, then this feature will sum to the total number of additions for a sentence. So it's a nice additive feature. Features should, in theory, be additive in a log linear model. Quite often they are not. But the Levenshtein distance is an additive feature, so this is a good thing. This feature has been used by us in the CoNLL Shared Task and also by the running team. And the same feature has been used by the Shared Task organizers in the later paper. This just showed that it was quite helpful. And another thing that we were planning to use during the Shared Task but never did was to split those distances into separate edit operations. So instead of counting how many edits are there, we count what edits are there. So in the first part, we have a deletion. So here, for instance, the A is deleted. We have an insert, what is being only is being inserted, and we have a substitution. No, sorry. yeah, time and term is being substituted probably. Okay, and just like that. And another thing that we did, we didn't really implement that, but if it hadn't been already there, we would have implemented it. A quite interesting thing is the operation sequence model that has appeared in Moses quite recently. The operation sequence model is being thought of as a reordering model, actually. But we do not do any reordering. So for us, it becomes an operation, it becomes an edit sequence model. We throw out all the reorderings because we do not really reorder. Also, the operation sequence model needs to invert source and target. This is just a design choice. It doesn't change anything. And the interesting thing is it creates a sequence of bilingual operations. So for instance, the first operation here would be that hence is translated to then. Then it says delete the comma. Then it says translate A to A, new to new, problem to problem, surface to comes, insert out, and translate the full stop to a full stop. If we now abstract away from the translation context and see this only as edit operations, then we have here a substitution, deletion, a match, again a match, substitution, insertion, and a match. So basically this becomes a sequence of edit operations. And if we now turn that into a language model, Ngram language model, then we have a stateful feature over edit operations. Usually the operation sequence model would also include operations like skip or make a jump of 5, then go back and everything. But since we do not enable reordering, so we use Moses without reordering, those reordering operations do not appear, and we have a very nice language model on edit operations. So now, what's the effect of that? The first thing what we did was to re-implement the Susanto system. This is just vanilla Moses, optimized using Bleu, which is not a good idea, but that's what they did in their paper. And it turns out that we get a result which is quite close to their results for their single systems. Then we add the Levenstein feature, which they also used, and again, we get a result that is quite similar to their result. Here we add the edit operations, so not only the Levenstein distance, but the Levenstein distance split into different edit operations, and here we are already better than them. And finally, the OSM, which seems to do not much in that moment. But this is actually, let's say, this is a wrong implication, actually, because what they did, they optimized with Bleu. They optimized with Bleu because, actually I don't know why, because my optimizer for the M2 metric was already available. They could have just used it, but maybe it was too difficult to use or something like that. Bleu optimization is already built into Moses, so it's quite easy to use it, but it's not the right choice because what happens if you optimize with M2 is this. So you get for free a huge improvement on the same development data with the same training data. And it turns out that the vanilla Moses with nothing else, just tuning for the metric, beats already their best system, which has classifiers and system combinations and I don't know, whatever. And this is just vanilla Moses without any additional task-specific features. And it's already better than their best system. And it seems that adding those additional features is not really helping much, but this is another mistake that we've learned, that the SMT community has already learned to do. Do not only look at one data point when you're tuning, but tune more than once. This is based on work from Jonathan Clark. So you should tune at least, I don't know, 3-5 times, and then take a look at average scores. When we look at average scores, we see an entire different picture. So we see quite clearly that all of the task-specific features help quite nicely. And another thing that is really helpful, at least for the grammar correction setting, is to average the weights. So you get a set of tuned weights after each tuning step, and if you average those, it turns out that at least when you optimize with the M2 metric, the result of the average system is better than the average of all systems. So, and this is a really good thing, because this means that you have a very easy choice which set of weights to actually choose. Because if you don't have, that, then you have a set of 5 weights, and you have an unseen test set, and the question is, which one do I choose now? Do I choose the best one? This is usually a bad choice, because the best one is quite often over-fitting to the test set. Do I choose the worst one then? This is also a bad choice, because the worst one also is quite often the worst one on the test set, so maybe just choose one that is somewhere in the middle. What do I do there? And it turns out that averaging solves that problem, because you really always get one that is better than the average, and in this one crazy situation, you even get a result that's better than the maximum. So, and this happens quite often with the M2 metric. I think in 200 experiments, I only saw once that the average system was a tiny bit worse than the average result. So this is like a...
The left side?
Yeah, but this is tuned with blue. So this is tuned with the wrong metric, and you cannot really say what's going on there. But for the M2 metric, this happens nearly every time. Like, I don't know, 99 times in hundreds, so it's going to be at least as good as the average. So it's like a really fair bet to choose the average system, because you cannot really go wrong there. Another thing that you should do is, okay, so how do we look by now? So if we look at the restricted system, we are already outperforming the top results for all restricted systems by now. It turns out that the vanilla system is already outperforming. So this little blue dot is vanilla Moses tuned on the right metric, and it's already better than the top result for now. And we can improve on that a little bit by adding task-specific features. Another question is now a choice of development set. The problem is that those development sets and test sets that have been used are incredibly small. Those are only 1,300 sentences, and within those 1,300 sentences, there are only 3,000 error annotations. So this means that only in 15% of the tokens in this small test set or dev set, there's actually anything going on. Because for all the rest, you just have to reproduce the input if you do not want to introduce errors. So this is very little data to tune a statistical machine translation system on. But the good thing is there's also the training data, NUCL. NUCL consists of 50,000 sentences with 40,000 error annotations, but the rate of erroneous tokens is much smaller. So roughly 6% of the tokens are actually errors. So this is again a problem, because if we now say, okay, this is small, let's just use NUCL for tuning, then we have a problem, because the main parameter, which is the rate of errors, is very small. So we might actually tune a system that will learn, okay, do not correct too much, because you might damage the data too much. While the dev set, at least, says that the error rate is much higher. And when I was looking at NUCL, where's this low error rate coming from, it's not so much that the students are much better. It's just that they copied much more from the topics that they were writing. They were writing topics on press articles, and they quite often just did copy-paste. So I was able to find the original articles where they were writing about. Also, they often have references. So they say, okay, this text is based on this and this URL. And now you have a URL which consists of 7 tokens, and there's no grammar error in the URL. So this is kind of a problem, but the system will still learn, do not correct the URLs, or do not change the URLs, because you're being penalized for that while you do the tuning step. We are also not supposed to look at the blind test set, but just to be complete, the error rate is around 10% for annotator 1 on the blind test set, and around 12% for annotator 2. So it's still quite close to the error rate of the dev set. So what we decided to do was to, and what we can do, we cannot do that with machine translation, is to greedily remove sentences from NUCL until an error rate of 0.15 is reached. This is quite easy. So we just remove correct sentences, and the error rate will go up. So in the end, we have around 23,000 sentences with 40,000 annotations, where the error rate is quite exactly 0.15, so quite exactly the same as in our dev set. We don't use the def set anymore because it's quite nice to have a second test set, because the original test set is also very small, so we could use that for testing other things. And then we do cross-validation on that. We train on 3 parts of knuckle and tune on 1 part, repeat that 4 times, and again we average the weights and repeat again a couple of times those steps to have 5 data points to be able to write those box plots. Already said that. Yeah, and another interesting implication from that could be, can we actually adjust the error rate in the training data too? Not only in the tuning data, but in the training data. So we would have one number that actually allows us to adjust precision and recall of the resulting system. And make the system, for instance, more greedy in concerns of corrections or less or more conservative, so that it won't correct too much. So what's the effect of changing the def set? This is the result for the previous def set tuned with the MaxMatch metric, and this is the performance jump just by choosing a different development set. And this is not really surprising because it's just a certain amount of data that you have to reach when you go through that tuning step. 1,300 sentences is barely anything. Just imagine for a moment that you would try to tune sparse features on that, 1,300 sentences, so you'd probably gain nothing from that. But with this better tuning or bigger tuning step, we are much more ahead. And if we now compare, it moves up our entire system, restricted system performance again by 0.5% probably. Interesting, expanding the search space barely helps. So just going up from 1,000 to 10,000 hypotheses during cube pruning barely does anything. The improvement is in the lower 2 places behind comma. And this is an interesting result because of this. Self-composition does help. And this is interesting. Self-composition, this is something you cannot do with machine translation. This just means, okay, take my output and give it to me again as input. So just let's run several iterations of self-composition. And this helps quite a lot. This helps nearly as much as adding a task-specific feature. So this is just the thing that you should do every time you do grammar correction. Just let your system correct its output once more. And why is this interesting in these 2 contexts? I would actually expect that enlarging the search space would also lead to an improvement similar to doing self-composition, because it's basically just doing the same thing again with the same data on a similar search space. It turns out it's not. So obviously the self-composition is producing some inputs or outputs that enlarging the search, that do not appear in the normal search space. What's exactly going on there, I do not understand, but I know that you've been doing similar experiments with factor-based translation, trying to get the factors into a second step. But I think it didn't really work, didn't it?
It's really tricky to get this right, because if you, like in the intermediate step, you forget your input, but you lose some information from the input, and
yeah.
The second step, if you don't choose the right granularity of what you really want to transfer into the intermediate step.
Okay, yeah, here it is easier because we do not lose anything. So we get a better input, and we just have to keep the good stuff and correct the stuff that's still wrong. So we do not have that problem. So maybe this is also the reason why this actually helps in this area. There's something about sparse features. This is something in our CoNLL shared task submission, we reported that sparse features do help. But by now, I would have to to back out of that, because the improvement that we saw was not because of the sparse features, but because of the tuning setup that we used in order to be able to use sparse features. Once I figured out that I should maybe try to see what happens if I switch the sparse features off, and we got the same improvement for that, then it turned out that it was actually the tuning scheme that was improving the results. You saw the tuning scheme earlier, and not the sparse features. But I still strongly believe that for grammar error correction, sparse features can help, because we will see a little bit later, they are able to model nearly everything that's going on there. So in machine translation, we have the problem that a lot of things are going on. Reordering, translation, length changes, and so on. In grammar error correction, we don't have this problem so much, so we can really use sparse features to encode nearly all of the actions that are happening. But the problems are right now of a technical nature. It seems that the tuning tools that work with sparse features are not working well with the metric. K-Batch Mira does something very weird. It goes up in the first iteration, and then it goes below the initial score in all other iterations. It does something like that. And I really do not know what's going on there. I'm still looking whether I made an implementation error or something like that, but I'm not seeing it. So I will have to contact the author of K-Batch Mira. Then what's also interesting, for the M2 metric, both Pro and K-Batch Mira give worse results than MERT when used without sparse features. While for machine translation, they are quite on par. You get sometimes better, sometimes worse, but in the average case, it doesn't make a difference. While for the M2 metric, I get around 2% worse with Pro and K-Batch Mira. And I do not know why yet. Interestingly, though, when I add sparse features, then Pro is able to level that out. So with Pro and sparse features, I get similar results as with MERT without sparse features. So the question is, does this mean that if I fix Pro to have the same results without features as without sparse features as MERT without sparse features, will that mean that I will get better results with sparse features later? But I've got to admit, I'm not really sure what's going on there right now. I'm quite sure it's correctly implemented. It should just work, but it doesn't. Maybe Pro is really tailored towards Bleu. Something to be discussed with the authors maybe of those tools. Let's show you why I'm interested in sparse features. This is the same sentence that we saw earlier for the operation sequence model, and we can go through it in the same way. And this time, we can add a feature like that. It's again substitution, then an insertion. We don't do anything for those words that match, but we add again a substitution, a deletion, and a match. And these sparse features go into the tuning step. So the tuner, the optimization algorithm, can assign specific weights to each of these occurrences. So in theory, it should be able to discriminatively assign good operations, operation by operation wise. But it turns out that this is not really working. What we also tried, since those operations are maybe not really expressive, to add context. So let's say if then is substituted by hence at the sentence beginning and followed by an A, then weighted accordingly. The interesting thing is that happens, the precision recall rate changes a lot. So the F-score remains the same, but precision goes up into 70%, from 50 to 70%, while recall drops a lot. And I'm not sure this is actually a bad thing. It might be that this system is actually much better than the system that has the same F-score but higher recall and lower precision, viewed from a grammar correction perspective. But since we still have this stupid MaxMatch metric, which is not really taking account for that, I'm not really sure. Nothing beats the language model. This is a hard lesson. Unless the language model beats you, which happened to us, actually, as I will demonstrate later. So using Kernel-Haffield's common crawl language model is basically near impossible. After half a year, I still haven't found a good way to actually make it run on a restricted hardware. I would need half a terabyte of RAM to run anything meaningful on that. Yeah, do you have half a terabyte of RAM? Oh, we should join forces. I have space. So I've come up, you can filter the language model, but it's a bag of words filter, so the result is still huge. It still requires 1 terabyte of memory. I've now come up, since I don't allow for reordering, I could filter by a finite state machine, not by a bag of word models. And I'm getting close to getting that to work. And I think once I have that working, I should be able to actually use all the relevant n-grams from that language model for the test set. But it's such a huge programming effort that I haven't done it yet. Also, it's really small. It's really slow to put that 5 terabyte language model through a finite state machine takes a while. Especially since the finite state machine itself becomes so big when I start to minimize it, so I have to maintain a couple of thousand of them in parallel. So it's not really easy. So we do not know what the upper bound is actually. But what we did, we sampled a subset from the raw text data. We downloaded all the common crawl data, and we used the cross entropy difference filtering according to our training data. We ended up with some 200 gigabyte of raw text that's supposed to be really in domain. And this already gives very good results. So if we look at the results that we had for Wikipedia, for our best results so far, this is what we get if we just substitute the language model. And this is the highest jump of everything that we've done, any other tuning, adding intelligent features, spending hours on inventing, I don't know what ingenious methods, just turn out, add a huge language model, and you basically win. But this makes the task also unrestricted in this moment. And where we messed up, why we could have had this result on the Kernel shared task instead of our 35%. I forgot to filter for the new test set. I filtered according to the training data, I filtered according to the development data, and I forgot that I did not filter for the test set. So we didn't have the right engrams in the filtered down language model. And this is such a rookie mistake that I could bite myself, I won't tell you where, but several times. I was kind of hoping that since the result was actually already something like 1 terabyte, that the engrams will be there. But when I looked through it later, it turned out that we are missing lots and lots and lots of relevant engrams. And concerning that, we still had quite a good result, that we had a really bad language model. And if we would have just used the Wikipedia language model, which we also evaluated, then we would have won the shared task. But since we had this performance jump on our dev set, and yeah, sure, let's use that. We are going to win everything. But we didn't filter for the right test set. If it had been possible to use this language model just without having to filter it, it would have been very easy, but unfortunately, that was the mistake. So this is where we are now, I think, yeah. So a single system was already able to beat a system combination from the best 5 systems on the Kernel shared task, and it's still not much more than vanilla Moses plus a few additional features. But to be fair, it's also a really huge language model. Collecting more parallel monolingual data. So since we are going into the unrestricted task, let's see whether we can get more parallel data. That's the data that I've been talking about, LangA data. So we were able to collect twice as many sentences compared to the free data. And as I already said, it's legally and morally dubious to use that, but let's do it anyway. And it turns out that this improves the previous common crawl-based system by another couple of %. You will notice there's only a single dot. That's because the calculations are still running. I only got 1 iteration from the tuning process before the talk. Probably right now the 2nd iteration has finished, and the other 3 iterations will finish somewhere around 6 o'clock in the evening today. But so probably the end result is somewhere here in a electron cloud around its atom nucleus. It might be a little bit better, it might be a little bit worse, hard to say, but there's still a very nice improvement. So we can again say that in the unrestricted task, we managed to surpass 50% on the Kernel test data, and this is by far the best single system on this particular test set. And without any tuning on the unseen test set. So this involves tuning on the unseen test set. We do not tune on the unseen test set. The only thing that we could say is a little bit dubious is maybe this error rate adjustment on the development set. But I claim that we adjusted it towards the development set, not towards the test set. We can collect more data, actually. A very interesting resource is Wikipedia. Wikipedia edit histories. We've already done that. That corpus is available for download. So we have 14 million sentences with minimal additions. Like mostly those are inserting and deleting commas, so not that interesting. But if you filter out the junk from those 14 million sentences, you still have some 6 or 5 million sentences with quite useful additions that are substitutions of nouns or real grammar corrections and so on. We are currently thinking what to do with that. We haven't really managed to use it in any useful way. I was able to improve the grammar correction results by concatenating two systems, so giving the input of one system into a system that has been trained on the Wikipedia data. Since the domain is quite different from the shared task domain, it's a little bit difficult to get those two resources together. So this will also require a little bit of work for domain adaptation and everything. So you see all the body of knowledge that's there in SMT, domain adaptation, tuning, has a very nice application in grammar correction. There are other wikis. This will be really interesting. Wikimedia, the company behind Wikipedia, is also the owner of Wikia, and Wikia is a page of social Wikipedia, so you can just create your social wikis, not social Wikipedia. So you just create a wiki on every topic that you find interesting. And it turns out that there's 400,000 of them in different languages. The majority of them is English. And quite often those will be entries built by non-native speakers. Usually they are about animes and mangas. I don't know why. It seems to be a very popular topic across those wikis, but the language is probably more similar to the shared task, because there will be a lot of non-native speakers who are writing about their hobbies. It's not so restricted as Wikipedia. And the good thing, there's a local branch of Wikia in Poznań, in my home city, which I didn't know until a few weeks ago. And I have a student who is an intern there, so direct access to the servers and the people. I just need to ask him to get me into the company, and who do I need to press for the data. And the good thing is the format is exactly the same as the format in Wikipedia, so we have all the tools already finished. We just need to download those dumps and run it through our pipeline, and we have another corpus available. And something which I'm really excited to do, but I'm also afraid to do it because of the huge amount of data that we would need to process it, is to compare two Common Crawl revisions. So let's say take the latest revision from 2014, take a revision from 2013, and compare them page by page. Are there sentences that are similar, and how have they changed? So mining the whole internet for grammar corrections or something like that. Maybe I don't know when and how to do that, but I think that would work. But that's why I said it's kind of hard to get those resources. Machine translation, we have it easier. We just look for multilingual web pages and we download them and we are done. Now getting those minimal edits is a problem because there's a time aspect there. We need to have access to newer and older data, and we have to be able to compare newer and older data. This is quite difficult. Final lesson, the grammar correction community or task needs a better metric. I've been complaining about the metric during the whole talk. Let's see why. Well, the first thing and the interesting thing is when you think of a grammar correction task, the one thing that you really should take into account, or I think it should really be something like a motto, is do not harm the input and do not get worse than the input. What does this metric say about the input? The input assigns a 0 because it's an F score. So in the input, nothing has changed. So the funny thing is, if you just take the input and delete all articles, you get a positive result for the metric. And somehow I doubt that this is better than the input if you just delete all the V's and A's. And still you get something like 5 or 6%. So if we would just delete all the V's, you would be somewhere here. It would be better than a system that actually tried to do anything with that. So this doesn't really say much about the metric. And another thing, let's compare to BLEU. BLEU is a similarity metric. Let's for a moment forget that it's specifically tuned to machine translation. But it is a similarity metric. It tells you how similar your output is to a reference set. And the question is, should really the input be one of the most similar results to the reference? If we resort that, it turns out that there's only one system that produced an output that's more similar to the reference than the input. While all the good systems, the winning systems, were middle field, the winning system at all was actually the third to last or second to last. And the best system was one that would have been one of the last systems. And if we look at precision and recall, it's not really that, I mean, we can understand where this comes from. BLEU is basically precision. So it will favor all those systems that have high precision. But in a grammar correction task, we should also naturally favor systems that have high precision, because this system is the one that probably did least harm. It also didn't do much good, but at least it didn't gobble up our input any more than the rest. While I'm really concerned about the winner, who has also, I think, the highest recall. Does he? Yeah, the winning system has the highest recall and not the highest precision, so probably the input, their output is probably worse, a lot worse than the input would already be. So what grammar correction needs is a metric task and a human evaluation probably. They never did human evaluation, so we do not know whether this MaxMatch metric correlates to human judgment. I also think they are answering the wrong question. They are answering how many errors did I get, while they should be answering, is my output better than my input? So this is a different question that they are answering here. To sum up, proper parameter tuning is crucial. So by parameter tuning alone, we get a vanilla system from Moses to beat all other systems that have been reported on this task. Language model is the strongest feature. It's also very important to get that right, as it turns out. Okay, this I already said. With task-specific features and self-composition, we get the new top result for restricted data. With additional language model and translation data, we beat all unrestricted systems, previously published results, and system combinations just with a single system. That's nothing complicated, actually. And the new top result for that is currently 50.9. I still have to wait what happens today during the day. And the MaxMatch metric is highly dubious. So this kind of invalidates all the results that we had before, because if the metric is crap, what does this tell about our results? Funnily though, this system is also has also quite high BLEU results. So this system improves the BLEU actually. So maybe there's hope. There's still a lot to learn. So how do I properly tune sparse features with this MaxMatch metric? Or how do I kill the MaxMatch metric so I don't have to tune with it? So this would be maybe better. Is it a sensible metric at all? Where and how can I collect more parallel data? Maybe let's see what, since the language model has such a huge effect, what do the new language model techniques do, like neural network language models? Can I fully integrate machine learning methods? That's what I'm here for, with Walpole Levitt. And thank you very much. That would be all.
Thanks for the talk, and now it's time for questions. So we start maybe?
There was one question.
Oh, there was?
I think here.
Maybe just for clarification. So you didn't do any error label guessing?
No, that's not part of the task actually. I think that's the problem is that's kind of explains where the metric is coming from, because they at the beginning they did error labeling, so their precision and recall metric makes sense. But then at some point they switched to correcting it, and for correcting I don't need labels. I just need to correct the correction.
Okay, so there were 5 error categories in 2013.
Yeah,
And
28.
And I wonder, they were all given the same priority. They didn't have any weights.
That's
in the evaluation, right?
Yeah, that's another problem of the metric. That's a problem that has already been mentioned in literature, so that errors shouldn't be weighted the same way, because, I don't know, missing a comma is maybe not that important as getting the meaning of a sentence totally wrong because you're using the wrong verb or noun or something like that.
Or spelling error.
Yeah, exactly.
Could be not as serious.
Exactly. It weights them all equally.
Well, I'm wondering about JEC or understanding languages where you might wonder whether this is actually a spelling error or whether it is a Greenland error,
Yeah.
because a missing accent could be either. and it's hard to.
And we all know how sensitive we are to agreement errors, actually. So how it's a small mistake, but it really changes a lot in the sentence in our languages. Well, luckily, this is English, but we will go. My PhD student is planning to apply those methods to Polish as well, and he will have a hard time for. Well, the one top priority is now to kill that metric, because it's really an awful thing, and I think the metric is holding the field back, because no one really knows what he's optimizing there.
Okay, and then I was wondering how much would be the minimal amount of data that you would need for a system to work properly?
What we used, well, in the restricted task that I said, we had 2 million sentences from the Lang 8.
2 million sentences?
Yeah. Not all of them with errors. So, I don't know, about 1/3 of them probably contained errors. No, one third of them contained error annotation. For Lang 8, it's not the same. Many of them probably contained errors, but not all were error annotated. And it's hard to say. It really depends on your task. I mean, from this Wikipedia corpus, we have a quite big resource that has tens of millions of sentences. But we weren't really able to use it for this task, for instance, since the language is very different. Then other teams already had some reasonable results with just using the NUC corpus, which is only 50,000 sentences, but meticulously hand annotated. So it is a very expensive resource to produce.
Well, I'm wondering about our learner corpus of Czech.
Yeah.
Well, the part that is manually annotated for errors is about 300,000 words. And this
some 20,000 sentences maybe. And that's error labeled. And and have you stuff that's corrected but not error labeled?
Both.
Okay, so yeah, because for this approach you don't need the labels. The machine translation approach just needs the.
The rest is not error labeled and it's not correct.
Ah, okay, it's just errors. Okay. Or you just don't know what you have, in other words.
Yeah.
Okay.
We have used a grammar checker for the whole stuff, which is about 2 million, including text written by people that are actually come from the Roma communities.
Mm-hmm.
Check it out 100% standard, and the non-native part is 1 million. And then we use this grammar spell checker, and I counted just on a small sample that if I take only the words that were not identified as proper Czech, that they were not recognized by the morphological analysis, so it gets the corrections right in about 80%. So
how much?
Well, 80%.
80%.
Of those words were corrected properly.
It's quite impressive.
I think we should do this MaxMatch evaluation.
Yeah. I mean, I still haven't made up my mind about the metric. It kind of makes sense in some scenarios, but when I see this last table, I really get huge doubts. Where is it? This is worrying. This is extremely worrying, in my opinion. This is the last column is just a similarity metric. You could use any other similarity metric, something that's maybe word error rate based, or something that's TF-IDF based, and you would probably still get a similar ordering of that. So something is not quite right with this metric, or they are just answering another question.
Thank you so much. I'm sorry about taking too much time.
Just that we think, can you go back to the list of errors?
Yeah.
So is there a type for spelling errors?
There is one for spelling errors.
I'm wondering how.
That one.
Okay.
punctuation and spelling.
And you didn't do
We didn't do anything about it because it turned out to be freaking hard. Whatever we tried, our results were worse than without doing anything. We had two problems, capitalization and spelling. So what we did for capitalization was we just projected the capitalization from the input on the output, projecting it. That's easy because you can just diff it. And whatever we tried to correct capitalization just didn't work, mainly because the capitalization was more or less random. English is really difficult for capitalization because they just start to capitalize things how they feel instead of capitalizing it with sense. Then they have title capitalization, which is something that is nearly like a pragmatic feature, basically. How do you know that you should capitalize the title? It's pragmatic knowledge. You cannot expect the system to know that. So we just didn't do anything with capitalization. And for spelling correction, it turned out that some of the data contained actually, so some of the things were automatically spelling corrected because it saw these errors.
Unless you actually see the correction in your own data, you are not able to correct.
Yeah, exactly. We only did so we didn't do anything for that. If it happened that it was corrected, then it was by chance.
The way how you treated out of vocabulary words in
We didn't.
Moses, you didn't. So you just copied, but you don't know you copied.
Exactly.
Any
Not at all, but I think if you do a monolingual task, then copying everything that you don't know is just a reasonable thing to do, in my opinion. So I never looked at that.
So maybe in that case you could use the usual spell checker for the OOVs.
Yeah, probably, but it is a little bit.
Close.
But isn't this dangerous? Because if you have an OOV in a grammatical error task, I think I would rather keep the OOV than. No, I don't really. Yeah.
One thing is a proper OOE from Moses.
Yeah.
And the other thing is the OOE in
From the
terms
spell
of
checker.
language, like unknown words.
Well, I let my PhD student play around with that, and we spent like, I don't know, 3 or 4 days on that, trying to see with different spell checkers, and whatever we tried, it was always slightly worse. We weren't really able to improve the metric on that. So we just said, okay, let's not touch it, let's leave it. I'm sure that it should be there somehow. I mean, it's natural. You should have something like a spell checker there, but we didn't really succeed. So whatever we tried, it was always worse. It was over-correcting.
I'm actually not surprised that it didn't work.
Yeah.
Because I think that especially English, the link between in Czech or Polish, it might actually work if you find OV in terms of language
Yeah.
guessing somehow what form it should be, because there's at least some reasonable link between spelling and phonetics. But
And we also have words
in
like
English,
that.
these links are so convoluted
Yeah.
between phonetics and between pronunciation and how things are actually spelled, that people often make errors that are actually not trivial. It's not just one letter that should have a different accent or something. So the grammar checker papers, at least some of them, show that you need basically transformation of string to any different string to capture errors that non-native speakers make.
Yeah.
So it is actually quite a hard task to correct spelling, or if it's an existing word.
That's right. So we gave up on
Those
it.
words like Shakespeare, people who cannot speak English, they might spell it completely wrong.
Do I know how to spell Shakespeare?
So I'm not really surprised. So I think that copying is actually might be sensible.
Shakespeare himself was not sure how to
Shakespeare is actually transliterated in Polish.
Yeah, it is. That adds to the difficulty, actually. Okay.
Any other questions? Okay, maybe I would like to ask, You mentioned that you, in the future, would like to make a diff between the common crawl versions
Yeah.
and see if there are any sentences that are very similar and have some corrections. But do you really expect that these are like grammar corrections? Does internet do grammar checks?
The funny thing, we don't really need grammar correction. What we just need is a reasonable amount of noise in the training data.
Okay.
Because the problem is we need alternatives. We need something in the phrase table which is a reasonable alternative. And the language model takes care of the grammar. So there don't always need to be grammar mistakes. So for instance, what we could also try to use is, and I'm going to do that, would be paraphrase corpora. Paraphrasing thing, because you will often have substitutions of nouns to other nouns that are synonyms or stuff like that. You should have probably added a synonym lexicon as training data. That might have been a good idea.
And would this help you on the test set for this task?
I have no idea.
Oh, okay.
Let's see what happens once I've done a diff on the common crawl, which I find scary.
Sounds scary. How much data is it? It's like hundreds of gigabytes.
Yeah, but they always they always report this huge number of terabytes of data, where they actually sum all the crawls together. So it's not that much, and it's conveniently chunked into pieces. So you can just kind of download it online, process that one chunk, keep the stuff that you want, and keep proceeding. So it is possible. You might need some, I don't know, 20 terabyte of disk space or something like that, and you get through it.
Thanks.
So if I understand well now, so you probably could just generate a lot of data by alternating the null numbers in the
I find that dangerous. I could.
So like if your assumption is correct that the language model takes care of everything, so what you need to do is just always try to make the noun either singular or plural and then see what happens. So
That has been tried. So error generation is not a new idea. There has been some success with that. I haven't tried it myself yet. In the CoNLL-2014 Shared Task, there was a paper that used that with statistical machine translation, but they got the tuning all wrong. So you cannot. They said it doesn't help, but they also said adding a bigger language model doesn't help. We saw it did. So without tuning, we cannot really say what feature helps. So I don't know. Maybe you could generate additional data. I'm a little bit against that, because I would rather use naturally occurring noise than adding noise myself. Because where do we generate this noise from? You probably generate it from pattern that you saw somewhere else, and then at some point you are probably starting to bite into your own tail. I don't know. Something to try. Yes.
Yeah, just about those other resources like Wikipedia edit histories.
Yeah.
Isn't it the case that most corrections are actually factual and not grammatical?
It depends. I mean, if you do small, if you collect those small edits, if in one sentence one word changes, it's hard. It can be factual, but this doesn't matter that much, because we have those features that can distinguish between the bigger. It can penalize a big distance between the source and the target phrase, and if you just get the right kind of noise, it might still be helpful. For instance, I did some experiment. I didn't mention it here, but if you use the full phrase table without pruning, you have for some words 10 of thousands of alternatives. Usually you cut it in machine translation, we cut it down to 100. It turns out that when we cut it, it hurts the performance. So this long tail of something that we would just say is noise still has some impact on our performance. So this is quite weird. I don't quite know yet what's going on there. So this would require some more research. Why is noise helping, and what kind of noise is helping, and does any kind of noise help? Can I generate noise? I don't know, but it turns out that keeping noise is a good idea. Getting rid of it, well, but that's another thing with the MaxMatch metric, because noise increases recall and lowers precision. So maybe it's a good idea to get rid of the noise, because you would get higher precision then. Still, it has all be seen in the context of the metric. And since we don't, in my opinion, don't have a good metric, I cannot really answer the question correctly.
Just a small note to the Wikipedia edits. Have you tried using the comments in the edits? For example, look if they contain, I don't know, corrected
I didn't do it
or
personally, but I think my PhD student who did that did that. At least for vandalism and stuff, because there's quite often vandalism that's actually worse than the original input. So I saw some, I don't know, Princess Di is stupid or something like that, and you don't want stuff like that in your minimal edits. So he did look at some meta information there. But it's quite difficult because you would need some kind of natural language understanding to find out what the person is actually commenting on. And yeah, this is easy, but this is like sentiment analysis. Oh, I like this movie so much. What a crap! So was this a positive or negative review? Because again, yeah, it's hard. But he did do something like that. I don't know the details.
Just one silly idea. Could you use your grammar correction system to edit the output of machine translation systems into English?
I'm not sure. I'm afraid that the type of error is very different.
Yeah.
And things like that, I think, have been done on in-domain data. I think they did machine translation output with correct references and trained systems on that. And it was not that good. But on the other hand, the distance between the machine translation output and the reference is quite big. While in our case, the distance is quite small. So maybe it would help a little bit. It's something we would need to try. I haven't tried it yet. I've been thinking about it too.
Yeah.
It's kind of, it comes naturally, kind of.
Yeah.
But I haven't tried it yet.
About a world where only a language model would be used without a translation model, like what's the baseline if you just try somehow generate all possible edits and rank them with the language model? Like, you know,
this is being done, I suppose, but I don't know what the...
Like,
I think one of the several of the Kernel shared task submissions did something like that. I think they used even tree-led language models or something like that. So they were somewhere in that range. Hard to tell, actually. I can't give you any numbers.
I can expect that for the spelling errors and for the determiners, it could be easy, like generate all the possibilities and rank them with the language models.
This is not very different from a vanilla Moses setup in that moment. You have a phrase table which generates the alternative and it gets scored by the language model. This is basically the same.
Yes, well, this is based on your motivation that maybe you need just some noise in the translation model to generate alternative. So let's clearly generate the alternative without like guessing the probabilities of the alternatives.
Yeah, I did that for casing, for true casing. So I just generate the uppercase, lowercase, and put that through a language model. This works very nice. I haven't done that for. I've thought it might be a way for error correction, for spelling correction at least too. I haven't run it yet. There's a very nice tool, again by Kenneth Heffield. It's called, yeah, exactly, Lazy, where you can do that very easily. You can write text format hypergraphs. You can just put anything into that and put the hypergraph through a language model to find the best path. And this could be used exactly for that. I've been also thinking how to employ that because you could also use the hypergraph generated by Moses and just annotate it with an external tool with some additional possibilities that come from other systems and then use that as a system combination. It would probably also be very nice.
Okay, so if there are no more questions, then let's thank the speaker again.
Thank you very much. This was the greatest number of questions I ever got after a talk.